Hi, this is Venkatesh from Tel Aviv University, and I'll talk about polynomials, divided differences, and codes. To begin with, we are concerned with error correcting codes, which allow us to transform a message, say of length k, into code words of length n via structured injective maps. And the length of the code word n is expected to be large enough so that we can allow for errors introduced by the channel and still decode from those to recover the original message correctly. So formally speaking, a code is simply the image of the message space and is a subset C contained in sigma to the n, where sigma is what is called the alphabet of the code, which is simply the collection of all possible elements that can appear as bits of the code word. We will be interested in what are called linear codes, which means the alphabet sigma as well as the code C are vector spaces over a field of Q. And in this case, the message space turns out to be a k-dimensional vector space, fq to the k. Therefore, the rate of the code, which measures the amount of information that can be transmitted, we will always denote it by r, turns out to be the fraction k by Sn. In order to measure the separation between code words, we will consider the distance function, which is called the Hamming distance, which is defined to be the relative fraction of coordinates on which the two code words x and y differ. And the smallest possible such separation between any two distinct code words of code is called the minimum distance. We will always denote it by delta, and since we are interested in linear codes, delta turns out to be the minimum separation between any non-zero code word and the zero code word. And there is always a trade-off between the rate and the distance. When the rate increases, we are packing in more code words within the code, and therefore the separation between any two distinct code words decreases. Formally, the rate versus distance trade-off can be captured by what is called the singleton bound, which says that delta is always at most 1 minus r. Codes which actually allow for optimal separation, that is delta equals 1 minus r, are called maximum distance separable codes, in short, MDS codes. We will be interested in a paradigm called list decoding, where we allow for a fraction of errors that is so large that we may not be able to recover a unique correct message from the corrupted code word. Instead, we can only hope to recover a small list of possible correct messages. And formally speaking, we'll say the code is row L list decodable if given any received word W within the radius, Hamming radius row, there are at most L many possibly correct code words. In other words, at most L code words have agreement at least 1 minus row times n with the received word W. And there is a version of the singleton bound which captures the trade-off between the list decoding radius rho, which is the amount of error that we can tolerate, with the output list size big L. So the list decoding singleton bound, which was formally pinned down by Shangwan and Tamu, says that rho can be at most L by L plus 1 times 1 minus R. In other words, if we specify that the output list size must be at most L, then the fraction of errors that we can correct from is at most L by L plus 1 times 1 minus R. So if we allow the output list size L to be something like 1 minus epsilon, 1 by epsilon, we can have the error fraction rho to be something like 1 minus R minus epsilon. That is epsilon close to the actual singleton bound 1 minus R. The question now is, are there codes which actually give us this kind of performance? And we will be interested in linear codes wherein the encoding map is defined using polynomials. So let's start with some basic polynomial code constructions from the univariate world. The prototypical such construction is what is called the Reed-Solomon code, wherein The message is really specified by a polynomial fx with degree say less than k, which means there are total k coefficients required to specify this polynomial completely, and these coefficients are the message bits. And the code word is really given by the evaluation table or the set of evaluations f at a1 to f at an, where a1 to an are some evaluation points chosen according to the requirement. There are natural variations of the Reed-Solomon code which pack in more evaluations within a single block. And two canonical such constructions are the folded Reed-Solomon code and the multiplicity code. In the folded Reed-Solomon or the FRS construction, we pack in evaluations not just at a point AI, but also at a set of correlated points AI, gamma AI, up to some gamma to the s minus 1 AI, where gamma is fixed to be a generator or more generally an element of the field with large enough multiplicative order. And in the multiplicity code, the encoding is another natural variant where we consider evaluations of the polynomial f at AI as well as its derivatives up to order some s minus 1 at the point AI. Note that at each evaluation point AI in the FRS as well as the multiplicity encoding, we bunch up these evaluations together into a block. So the alphabet size increases from the size Q, which is the size of the field, to Q to the S, because there are S elements bunched up together, forming one bit of my code word. Why are these folded constructions interesting? It's because intuitively what we know now is that bunching up bits of a code word allows us to increase the list decoding radius or allows us to decode from a larger fraction of errors. So what do we know about list decoding such polynomial codes? This is a small sample of the state of the art that we know. So in case of the simple Reed-Solomon code where there is no folding, Guruswamy and Sudan showed that there is an algorithm that allows us to decode up to the Johnson bound, which is radius 1 minus square root r. But we know a complementary result by Ben Sassoon, Koparthi, and Radhakrishnan, which says that there are explicit Reed-Solomon codes which cannot be decoded up to capacity, that is radius 1 minus r minus epsilon. In fact, this result says that such Reed-Solomon codes cannot be list decoded up to any radius that is significantly beyond the Johnson bound. So Johnson bound is really almost the limit of efficient list decodability. And in this case, the list size turns out to be a constant that is dependent only on the rate. And we are interested in such performance where the output list size is really a constant, which might only depend on the gap to capacity epsilon and nothing else. The folded constructions, the FRS code and the multiplicity code, we now know can be list decoded up to capacity, in fact. And previous results by Guruswamy, Rudra, and Koparthi, and Guruswamy and Wang gave us list decoding algorithms which promised an output list size that is polynomial. And later, Koparthi and a few others, as well as a slight improvement by Tamo, showed that the output list size guarantee can in fact be reduced to be a constant, which is exponential in 1 by epsilon. The state of the art that we now know, which is some very interesting development from just last year, in fact, promises that the output list size is in fact the optimal constant linear in 1 by epsilon. Nevertheless, the best algorithm that we know is still the previous algorithm by Guruswamy and Rudra for FRS, Koparthi for multiplicity codes, as well as the algorithm by Guruswamy and Wang, which is really a linear algebraic algorithm that works for both FRS and multiplicity codes. Our interest is in this linear algebraic list decoding algorithm, which says that when the folding parameter S is roughly 1 over epsilon squared, FRS and multiplicity codes can be list decoded to capacity. But what is hidden here is an important feature, which is that for multiplicity codes, we get this list decoding performance if the characteristic of the field is large. In particular, it needs to be at least as large as the degree parameter. In fact, this restriction is necessary the result by Ben Sassoon and others, which showed that there are counter examples to list decoding Reed-Solomon code beyond Johnson bound. We can actually lift these counter examples to give counter examples for multiplicity codes as well when the characteristic is very small. However, such a pathology doesn't arise when we consider folded Reed-Solomon codes. These are list decodable up to capacity without any such restriction. In other words, the list decodability of FRS codes is insensitive to field characteristics. And it is this insensitivity that we are really interested in. Let's quickly look at what happens in the multivariate case. Something very similar happens. So in the multivariate case, again, similar natural constructions are the Reed-Muller codes, which is simply a multivariate analog of the Reed-Solomon code, wherein the message is again a polynomial with a degree bound, and the code word is simply a list of evaluations of this polynomial at a set of points. The set of points needs to be nice enough, structurally nice, and we will consider it to be a finite grid, let's say a to the n. And the folded version now is the multivariate multiplicity code, which is simply considering the evaluations of the polynomial as well as its partial derivatives up to a certain order s minus 1. Once again, we know that the Guruswami-Sudan algorithm for list decoding Reed-Solomon codes can in fact be extended to also list decode Reed-Muller codes up to a radius 1 minus r to the 1 by m with constant output list size. And a very recent result, which is of interest to us, by Bhandari, Harsha, Kumar, and Sudan, showed that if S is like 1 by epsilon to the 2m, where m is the number of coordinates, the m-variate multiplicity codes can also be list decoded up to radius delta minus epsilon. That is list decodable up to distance, where delta is the distance. Again, we encountered the same pathology that we require the characteristic of the field to be larger than the degree parameter, and this also turns out to be necessary. We can in fact lift the counterexample that we have for univariate multiplicity codes to even the multivariate multiplicity codes. We can construct similar counterexamples when the characteristic is small. This brings us to the question, is there a characteristic insensitive variant of the multiplicity codes with similar list decodability? Also, so far, something that we have not seen in the multivariate case is an analog of the folded Reed-Solomon construction. So can we extend the univariate FRS codes to the multivariate setting? These are the two primary questions of interest to us. In fact, we would like to understand a construction with similar list decodability that also has a good list decoding algorithm. And the answer to both of these questions is yes. So the key observation to our result is that the univariate FRS code itself can be interpreted as a multiplicity code with respect to a suitable derivative operator. In fact, it turns out to be a discrete derivative or a divided difference. And once we make this observation in the univariate world, a simple multivariate extension also gives us the characteristic insensitive multivariate construction that we are looking for. It turns out to be a divided difference code. So what is this divided difference? Before we go into the code construction, this turns out to be something that's called the Q derivative. It's also a very classically understood linear operator. In this case, we choose Q to be just the generator gamma of the multiplicative group. The Q here really is a placeholder. It can be chosen to be whatever element we require. We will make the choice that Q is the generator gamma. And for any polynomial fx, the gamma derivative turns out to be this divided difference, which is just the ratio of f of gamma x minus fx with gamma minus 1 times x. And we'll denote this by d gamma. What is interesting to note is that d gamma is very similar to the classical derivative operator, in particular for a monomial x to the t. the gamma derivative of x to the t turns out to be a scalar times x to the t minus 1, where the scalar is simply the fraction gamma to the t minus 1 by gamma minus 1. In particular, what we see is that if the degree of the polynomial is at most q minus 2, then the degree of the derivative of f with respect to gamma is equal to degree f minus 1. This is similar to what we observe in case of the classical derivative, but what is important here is that the degree is exactly equal to degree f minus 1. In the case of the classical derivatives, if the characteristic of the field is small, the derivative of a high degree monomial could actually be just 0. That's the pathology that uh, leads to the requirement of characteristic being large for the list decodability results. Whereas if we consider this discrete derivative, that pathology does not arise. Even over fields of small characteristic, large degree monomials will only have the derivative reduced by 1 when we differentiate with respect to gamma. Okay, so the Q derivative is not really a new discovery. It has found applications in a large field called Q combinatorics. Uh, Good references are by Extend and Roman, as well as quantum calculus. A good reference is a book by Ernst. But usually it appears over fields of characteristic 0. And this is really a multiplicative rate of change, as we have defined it here. And this definition has not really found any explicit appearance in the polynomial method literature, to our knowledge. In this work, in fact, we will instantiate the Q derivative over fields of small positive characteristic and very well within the framework of the polynomial method. So this might be of independent interest. So let's quickly look at some basic properties of the gamma derivative, which shows that this is very similar to the classical derivative with some subtle differences. In the classical case, we have this Taylor expansion. For any polynomial, we can write it down as the usual Taylor expansion as long as the degree is less than the characteristic of the field. If the characteristic is really small, then we can replace the classical derivative with the Hasse derivative, the scaled variant. Nevertheless, the Taylor expansion remains nearly the same. In the gamma version, we have a gamma Taylor expansion, which now tells us that every polynomial can be expanded in this way, where once again we have terms which are very similar to the classical Taylor expansion. It is just that the monomials are no longer powers of the same linear factor, but instead it's a product of correlated linear factors, where the correlated linear factors are really multiplicative shifts of the beginning linear factor x minus e. And this Taylor expansion is now valid as long as the degree is less than the order of the generator. So the degree d is less than q minus 1. In particular, this Taylor expansion is insensitive to the characteristic of the field. This expansion is valid even if the field has characteristic 2. The similarities continue. For example, we have the classical product rule, which expresses the derivative of a product f times g in terms of derivatives of f and derivatives of g. We also have an analogous gamma product rule, which expresses the gamma derivative of f times c in terms of the gamma derivatives of f and g. So once we notice these similarities, it is obvious what the definition of a multivariate gamma multiplicity code should be. The encoding now takes a message polynomial fx to the collection of its evaluations as well as evaluations of its gamma derivatives up to some order s minus 1. And here we are looking at partial derivatives with respect to the gamma multiplicity operator, which is defined analogously. So simply apply the individual gamma derivatives iteratively. And now the analogous properties extend even to the multivariate setting. We have a gamma Taylor expansion as well as a gamma product rule for multivariate polynomials. So let's move on to the algorithmic result that we have. Our focus is really this algorithmic list decoding result by Bhandari, Harsha, Kumar, and Sudan, which said that M-variate multiplicity codes can be list decoded efficiently up to radius delta minus epsilon, where delta is the distance of the code, as long as the degree is smaller than the characteristic. And this condition is necessary. Our result says that for the same setting of parameters, the M-variate gamma multiplicity codes are list decodable efficiently up to radius delta minus epsilon. But now this list decodability is unconditional on the characteristic of the field. The degree parameter needs to be less than just the order of the generator gamma, which is q minus 1. In other words, the list decodability of multivariate gamma multiplicity codes is insensitive to the field characteristic. In particular, this even works when the characteristic of the field is 2. Okay. Another simple-minded interpretation of this encoding is as follows. It's very easy to see that if you look at the block corresponding to the folded Reed-Solomon encoding, which is simply a bunching of evaluations of the polynomial f at points a, gamma a, and so on, there is in fact a change of basis that maps the folded Reed-Solomon block to the gamma multiplicity block. In other words, there is a distance preserving map between FRS code and univariate gamma multiplicity codes. The same can be extended to the multivariate setting, and this analogous extension can be thought of as a folded Reed-Muller code. So there is a basis change that maps the multivariate gamma multiplicity blocks to simple evaluations where the evaluation points are now considered uh, with respect to multiplicative shifts in each coordinate. And this can be thought of as a folded Reed-Muller code. Okay, so we are coming towards the end. Let's quickly look at what the list decoding algorithm looks like. This is simply an algorithmic instantiation of the polynomial method. And this list decoding algorithm can be considered a gamma extension of the list decoding algorithm of Bhandari and others. And in this case, the technical details are even simpler because we are working with the discrete derivative. And we also think this can be considered a natural multivariate analog of the linear algebraic list decoding algorithm of Goswami and Wang in the univariate case. The main takeaway of this algorithm is that a simple folding trick introduced by Bhandari and others, coupled with the univariate list decoding analysis of Guruswamy and Wang, gives us the required multivariate list decoding analysis. Okay, so what does this algorithm look like? So consider an M-variate gamma multiplicity code over a finite grid A to the M. And let's say we have a received word W, which is indexed by the evaluation points A as well as the multi-indices corresponding to the derivatives alpha. We will use a folding trick introduced by Bhandari and others, which is really considering auxiliary variables Z1 to Zm, and we will consider monomials in these variables. So the first step is to capture the received word using a multivariate polynomial called the interpolating polynomial. And the structure of this polynomial is linear algebraic in the sense that we have the variables x1 to xm corresponding to the polynomial encoding, the variables y's which correspond to the bits of the received word, and we have these additional variables z1 to zm. The interpolating polynomial is linear in the y variables, which is why we consider this as a linear algebraic list decoding algorithm. It turns out to have exactly this form q tilde x plus summation over j qjx times this linear form in the y variables. And we capture the received word by imposing vanishing conditions of q. In other words, for every evaluation point a, when we consider the evaluation values wa alphas, we want the polynomial q to vanish at this tuple a comma wa alphas with high gamma multiplicity. In other words, the polynomial should vanish and its derivatives of high order must also vanish at this tuple but the derivatives are the gamma derivatives. So the vanishing is defined in terms of the gamma derivatives, which is why we call it high gamma multiplicity. Once this happens, what we notice is that the vanishing conditions will imply the following. If there is a correct code word that is close enough to the receipt word W, that is the agreement is large enough, then the projected polynomial QF, which is really defined by substituting the y variables to be the corresponding derivatives of f, the gamma derivatives of f, the projected polynomial Q sub f will have a large number of roots because every vanishing condition gives us a root for the polynomial QF. And since the number of roots is large enough relative to the degree of this polynomial must in fact be the zero polynomial by the degree bound. Therefore, since this polynomial has an affine linear structure because of the linearity in the derivatives of f, we can solve the equation qf of x equals 0 and obtain a solution space, which is really an r-dimensional affine linear subspace, where r is a parameter which is corresponding to the number of qj's that we take in the structure of this polynomial. And we choose r to be somewhat less than the multiplicity parameter s in order to get the correct list decoding radius. So we get the list of correct code words contained in this affine linear subspace of dimension at most r. And every correct code word fx is captured as a solution of such an equation. That is really the outline of the list decoding algorithm. The technical details can be found in the paper. And this brings us to the end of this talk. Thanks a lot.